Today we have Goren Gordon here. Thank you for coming. Goren received his bachelor and master in physics and MBA in Tel Aviv University in Israel. His first PhD was in chemical physics at the Weizmann Institute of Science, where he researched dynamical decoherence control of open quantum systems and quantum communication protocols. His second PhD was in neurobiology, also in the Weizmann Institute. Together with Professor Achisar, he developed novel mathematical models of curiosity and exploration. Goren has more than 40 publications in several disciplines, most as first order, several as single order. He's currently working at the Personal Robot Group Media Lab MIT. In his research interests are models of curiosity in children and robots and their interactions. Today he's going to talk about biological artificial curiosity, models, behavior, and robots. Thank you very much.
Can you hear me? Yes? Okay. So first, thank you very much for inviting me, giving me the opportunity to talk about my research. So I'm going to talk about biological and artificial curiosity. To start with a quote that I like, which is, "A man of genius makes no mistakes. His errors are volitional and are their portals to discovery," which embodies the concept that I'm going to talk about, which is curiosity, which means you should make mistakes in order to learn more. This will be a main thread throughout the talk. So first I want to start with a basic framework of my research, which is 3 pillars of understanding. So if I'm interested in the behavior of animals or people, first need to prepare to have a model, preferably mathematical and as simple as possible, in order to describe the behavior. And then you go back and forth and improve the model and try to understand and predict behavior. But in order to fully understand, you actually need to implement this model in an artificial agent like a robot, and then compare the behavior of the robot to the object of your interest, which is either the child or the animal. And then you can compare and see whether the behavior that the robot exhibits using your model actually somehow correlates to what you're interested in. And recently there is actually a new field called human-robot interaction, which says what happens when the person interacts with this robot and when we're on the same ground. And I'm going to describe some of these work. So I'm interested in curiosity. So this is a curious agent. It's my baby girl, Noga. And as you can see, she's very curious about this object. This is unfortunately not my robot. It's called iCab. It costs $1 million and don't have it, but someday. And this is a film from my recent research, which is a curious child interacting with a curious robot, and see what happens when these two meet together. So why study curiosity? From the perspective of robotics, robots are going to come to our house and are going to interact with us. It's going to be a very complex and dynamic environment, and it will be very hard to program every behavior of the robot. Infants, on the other hand, learn by themselves a lot of abilities. They learn how to walk, how to talk, how to play, and we can be inspired by their behavior. By understanding the behavior of curious babies, we can actually develop robots that can autonomously learn different abilities, can have automatic recalibration and robustness. From the point of view of children, it's very hard to do controlled experiments with children, unless they're yourself, unless they're your own, but then you need to pass Helsinki and the mother. But again, you can use robots as a test bed for testing the models that you developed in a very controlled environment. So by testing models of curiosity on robots, one can infer maybe abnormal behaviors in the robot that can then correlate to mental syndromes. Or on the other hand, try to do environmental enrichment on the robot, see how it learns in those different environments, and then develop a guided development for children. And in this new area of human-robot interaction, it's very hard very unknown to have to study the interaction between curious robots and curious children. It's a very complex environment. But by building models of the social interaction, by assessing the children, maybe we can shape children's curiosity by having them interacting with a robot. And we can personalize the robot behavior to each child such that the robot grows with the child and learn together, and have them as a lifelong companion, not just LG cell phones. So I'm going to talk about curiosity a lot. So let's start with definitions. I have to start with definitions. So this is the Webster definition, the desire to know, which talks about the drive. I like this one better. It's interest leading to inquiry, because it actually talks about behavior. I'm interested in explaining the behavior. And here there's inquiry. You need to ask questions in order to be curious. So again, this child is very curious. It's actually behaving and exploring the world. And this is not a dictionary. This is me. So my definition is self-motivated action aimed at learning as much as possible. Let's decompose this sentence. So it actually integrates several disciplines from computer science. One of them is active learning. It's all about the action. It's the action that optimizes the learning process. You want to learn something, you need to act in order to learn it in an optimal manner. It's self-motivated, which means there's intrinsic motivation. So the reward comes from within. It comes from internal processing. And also learning as much as possible. So for a curious person, for every answer, there's a new question. So you have to have a hierarchical structure where you build upon what you learn in order to learn something new. And that hopefully will never stop. So this is the basic framework. And what I'm going to address now are two specific questions. One of them is what are the bounds on curiosity and exploration? What can limit exploration, or curious agents just go around and just explore as they will? What are the basic principles of freely exploring agents, and can we distill everything to one or two simple principles that can explain a large variety of behaviors? And the second thing is, can we shape learning-driven exploration? So exploration is moving in order to learn. Can you learn how to explore? And the second thing is, can this intrinsic drive be externally affected? Can someone affect a child's will to learn? And I'm going to address all of these questions. So the layout of my talk is the first one to talk about understanding the behavior using the model that I developed. First about information-seeking task in whisking humans, and I'm going to talk about novelty management in rodents. And then I'm going to move to robots, how I implemented the models, or these models, into robots. First about a robot that learns about itself, and then about a robot that learns to interact with other people. And finally, I'm going to show a movie and maybe talk about a little bit about my recent research, which is what happens when a curious robot meets a curious child in this interaction. So let's start. So in an ingenious setup contrived by Avi Saig from our group in the Edo group, he thought about why are we only using animals to model people? Why not use people to model animals? So he invented the whisking humans. So we're in the lab, we had rodents with whiskers where they explored the environment and said, why not put whiskers on people and see what they do? And they actually put them in a task that we put all our rodents, which are two vertical poles, and they need to localize the poles using the whiskers that they have. And he put two sensors, the position sensor and the force sensor, on the whiskers, so we have all the information coming into the system. The system here is a person. And what he showed is that they actually use the same motion strategies as rodents, which means they whisked with their hands and the artificial whiskers and tried to localize which pole is more posterior. So I tried to develop a model to see whether we can capture all of these behaviors in a relatively simple model. So the task is a very simple perceptual binary task. We just want to see which pole is more posterior. And so you have this probability, and you have a Bayesian update. Every time you touch the pole, you update the probability of which one is more posterior based on your perception. And what he showed, I'm not showing it, what he showed is they actually use not the position, the distance in position, but actually they synchronize their hands, and what they use is the difference in timing of touching the poles. So what they had is actually the temporal difference between touching the poles. That is what they used in order to update their perception. And what we have now is just the temporal noise. So how accurate is the sensing of the difference between when you touch the first pole and you touch the second pole? So this is again a Bayesian update, relatively simple question. And now we ask two questions. The first one, can we say something about how many times they touched the poles until they decided, okay, I think I know which one is more posterior. And now we have a new parameter, which is the decision probability. When did they decide? At what probability they decide? Okay, I think I know, and reported what they thought. So here is the results. The dots are the experiment, and the line is a fitting of the model with only two parameters. And two parameters have meaning. The first one is the sensory noise, which is the temporal difference noise. And it's 300 milliseconds, which is very comparable to other sensory noise. It's actually larger because this task is actually motor sensory. It's not just your receiving senses, which is the sensory noise is smaller. Here you actually move yourself, so there's also a motor noise. And this is makes sense. And also the decision probability is 82%, which is again comparable to other psychological experiments, we say this is around the probability where people report that they think what is angle more posterior. So this is the first question. The second question we thought about, we try to answer, is they have this very intricate behavior, their whisk. And they start to whisk with large whiskers and then smaller whiskers. Can we say something about this behavior? Can we try to explain what are they trying to do? So for this, we used optimal control theory. Usually, optimal control theory is used in motor planning, where you have to try to move a pendulum from one place to another. So you have like a goal from getting from one place to another, and then you have like an energy cost. This is usually what you have used. Optimal control here, it's a perceptual task. You want to get information. This is your goal. And then, so you have obviously energy cost because they move the hands. But from symmetry reasons, we introduced perceptual costs. So like we have energy costs, which are the second derivative squared, it's like the energy. And here you have a perceptual cost, which means it costs you to update. The more information you get, it somehow costs you. You want to get a little information. It costs you to get this noise.
Why don't you use measure of information?
I use that actually just from symmetry in this sense. I know it hurts your eyes, Sally. You're showing a derivative of probability. And this is what we used initially. So this we actually use just from the symmetry reasons. So we have a motor and perception exactly in the same reason. The perceptual. Wait 1 second. Why perception? We don't know why, but we just assume it and see whether this can explain the behavior. Huh? No, if you don't have this term, then it cannot explain the behavior. You have to add some other term than just energy cost. There has to be something else other than energy cost. And this is the first term in the development of approximation, the second approximation. This is the thing that you can have.
What exactly is the behavior that you're trying to? What feature of the behavior?
The feature of the behavior is that they're whisking, and their first whisking is very large, and then they're reducing the amplitude and the time. And as the result actually comes out, again, you have here the amplitude and the duration. The set point is the number of cycles, and again, this is the result, and this is the model with only a single parameter. And what you get from this optimal control is actually that the change in perception divided by the time, the duration of the actual time of each whisk is constant, which means they have the constant information flow. So initially, each touch gives them a lot of information, but it takes them a lot of time. And as they decrease the time, they get less information. But it comes about to have a constant information flow in the end. And this is something that we'll see in other places also.
When you say the time, when the frequency of whisking becomes...
Here, the duration of each whisk decreases as the number of whisks. So the take-home message from this study is that there are perceptual costs that lead to actively maintain constant information flow. Okay, we don't know why there are costs, or maybe there's another form, but you have to have something that balances just the energy cost in order to explain this behavior. Otherwise, the optimal thing will be completely different. Yes, here.
So why
is the information flow? This is the amount of change in the probability that you have. Let's take it offline later, okay? The second thing I want to address is the rodent exploration. So again, in a very interesting experiment done by Udi Fonio. Yes.
Did you test any predictions of this? For example, change the weight?
No, we didn't do any predictive experiment afterwards. We tried to explain the behavior in a very simplistic model here. So the second thing that we did is, again, we have an experiment that was done several years ago by Udi Fonio in our lab, and he put mice in a home cage where he provided everything they need. They have food and water, and then he opened the door to a circular round arena, and he just filmed them and tracked their behavior over 3 days to see how they explore the new arena. And this is, just to read this is the time axis, and this is the behavior, the motion inside the circular arena. And there's 2 things to notice. First of all, that the exploration complexity increases with time and along several dimensions. So first, this is like the 0-dimension behavior, which is just circle in place around the exit of the arena. And then it goes to around the wall, which is this first dimension, and only after they finished the circumference of the wall, they went inside, which is the second dimension. Only after they finished that, they actually start jumping and rearing, which is the third dimension. The second thing that you can see is actually each time they went out, they went back. So they went out, and then they went back, and then they went out, and then they went back. These called excursions, and the excursions changed with time, but every time they went out, they also went back. They didn't just go and explore everything. So first of all, we wanted to just try to analyze this behavior. Again, after the experiment, not predict, just analyze this behavior from an information theoretic point of view. To see what we can we say something about what is the novelty, what is the information and novelty within these patterns. So how can we model novelty in this situation? So we assume they're trying to map the environment or learn something about the environment. And we use the forward model. Forward model means that given the current state that you're in, you're doing some action. What will be the next state you're in? So, for example, this can also describe walls. So a wall is described using this. Is if I'm here and I'm moving right, and there's a wall to the right of me, then I won't move. So my state won't change. It's a very painful way to describe walls. But if you bump into walls, this is how you describe it. So this representation of probability distribution over states and action in the next state can actually describe the environment and the walls within it. So we assume they're trying to learn this. And how they learn it? So they have observation, they have their whiskers. The experiment was done in darkness. So they had to use the whiskers and touch the walls, and this is how they update the information about where there are walls. And because there is, again, noise in the system, the observation are not entirely correlated to the state, so there is some sensory noise. And what they do, they have this initial probability distribution, the initial map of the environment. They have observation, they update it, then they do some action, they move. They get another observation, and they update their probability distribution again. And now you can have some measure in information about how many, what did they learn about the environment. It's called the information gain, and it's the scale divergence between these two probability distribution. It measured how many bits they learned or updated about between these two probability distribution about the environment. We call this novelty flow because it's at each point in time you can actually have this. So each point in time there is an amount of information of a novelty flow, how much they learned about the environment. And we define the novelty as during the entire excursion, going out and going back, how much information flow did they get. Okay, so this is how we just took the trajectories of their behavior and trying to map them to novelty. So for example, this is an example. So we have here like because it was a circular arena, we did the angle and radius. So this is the trajectory, and this is the novelty flow. And these vertical lines are actually excursions. So they go out, they go back, they get novelty. And this cross is the first peak of the novelty of the novelty flow. So this is how we just map each trajectory to the flow of information that they have. And our question is, how do rodents actively control their novelty intake? So our question is about their actions. Why do they choose the actions that they choose? They can do a lot of things. Why do they choose the actions that they choose? And again, because we didn't do an experiment, we didn't have optogenetics at the time, so we couldn't just control their actions as we wanted. We did a post-hoc analysis of the behavior itself. And what we did is we did 3 controls of the actions. So we just scrambled the actions in 3 different ways. The first way is to have a long time scale shuffling, which means we took excursions, we maintained their internal dynamics, but just shifted their excursion. So for example, if the experiment they did a small excursion, then a large excursion, we just shifted their order. So this is one control. The second control is the random, which means we maintained the order of excursion, but within each excursion, we shifted the actions. And the third one is actually both of them. It's very important to note that it's exactly the same actions in all the controls, it's just the sequence of actions is changing. So the statistics and everything is the same, it's just the sequence of actions is changing. And we want to see what we can learn from comparing the experiment with these 3 controls about why or what is different between their choice of sequence of action and other possible choices. So the first thing we did is about novelty. So what is the novelty compared to other things? So as you can see, novelty has nothing interesting to say with regard to all the other things when you take the whole excursion. But if you divide the excursion to the outbound, where they go out and then they go back, you actually see that the outbound is much larger and significantly larger. They get more novelty in the experiment than all the other shuffles, which means it suggests that maybe they choose their action or the sequence of action in order to actually maximize the information that they get while they're going out. And that, again, it's not that surprising because they're going out to explore. So they want to get information from the environment. And the question is, what happens when they go back, or why do they go back? So in order to study this, we time align the peak of novelty flow So from all the excursion, we time align the peak of novelty flow, and then we measure the distance from the home cage to see whether what happens after they get the maximum novelty, how do they behave. And what we showed is that there's a novelty-based withdrawal-like reflex. So we have pain. When you have pain, you go back. You have a reflex to withdrawal. And this is what they have with respect to novelty. So when they get the peak of the novelty flow, they actually go back. And again, this is a significant difference than compared to all the other controls. So they go out in order to get as much information. When they get too much information, they actually go back, like a reflex. The third thing we analyze is that this unique environment of the arena has a structure of novelty. So the exit from the home cage is actually very complex. There's an opening there. There's a lot of information to learn there, as opposed to the walls, which is just a single wall and it's very simple. And the center of the arena is actually completely bare. So there's actually no novelty there.
Can I ask a question about this?
Yes.
So isn't it just because every time they go slightly further, it like less?
So it's not completely correct, because when they start to go inside, they don't go further. And there's sometimes when they go one direction and then they go the other direction. So it's not further. It's not just distance.
So how does this novelty measure relate to more natural things like pride?
There's a lot of definitions of how novelty is.
What's the relation?
Huh? Between surprise. So we define here the novelty as the information gain.
Information gain is related to what? It's a change in distribution.
Yes. It's how did they change distribution when they discovered new things about it.
Information gain is more or less okay, although I don't understand why you add them. These are not independent. So essentially it is expected probability, actual probability relative to expected one.
It's how they get a new observation. It's how much they update about their information about the environment. It's not related to the actual probability, because they don't have the true probability.
What is novelty? The behavior or the...
No, the novelty is the measure of, given the behavior and the new observation, how much did they update the information, their description of the environment. Because this is what they know about the environment. How much did they change their observation of the environment? So we discretize, the trajectory is discretized to angle and radius. So it's actually like a grid, a polar grid. And then we know where are the walls along this grid. And we know the real distribution, the forward model, because we know the real environment. And each time they take a step, we update that probability distribution the way they have. They started with uniform distribution of walls, and we just update every time they touch a wall. They are near a wall. Not I update the algorithm, the model updates. Yes, the average estimate from the behavior. The trajectory, yes, I say we convert the trajectory to this thing. Using the model, using the forward model. Yeah. We don't know what they actually. Yeah. We assume they're trying to learn the environment, and this is what we do. Yes. So coming back to the structure of the novelty in the environment. Again, we show that in the experiment compared to the control, they actually explore the more novel things first and only then. So there's the order of novelty that they explore. And all of these actually come to one result, which we think that is most important, is that they don't maximize the novelty within X excursion, but what they have is higher novelty signal to noise ratio, which means if you take all the excursion, you take the mean of novelty divided by the standard deviation across all the excursions, what you see is that the signal to noise ratio here is much larger than all of the other controls, which means they try to maintain a constant level of novelty. They don't want a large distribution. So for example, in the shuffle, in the shuffle control, you can have a lot of novelty and then a small degree of novelty, a lot of novelty and a small novelty. And you can see that actually the mean is higher, but there's a lot more variation. So what we showed here is that they actually, the experiment compared to the controls have a higher signal to noise ratio. They want to have, so the take home message here, there's a balance between efficient exploration. They want to explore, but there is some withdrawal from novelty. So there is a balance between no philia and no phobia. There are two drives here. One they want to explore, and the other one is too much information is also not good for them. And that leads to active novelty stabilization. So each time they explore the environment, they want to get the same amount of information. Novelty. Yes.
Previous model of taking into account the energy consideration, is it relevant this time?
I don't think it's relevant because it's very like short distances and they have foods. They're not like tiring here. They don't go again because they go to different, the completely different lengths at each one, and they don't. It doesn't relate to like the distance. All of this doesn't relate to the distance because the shuffle control we showed. It's not related to distance or the time from the home cage. So I don't think energy here plays a significant role.
Physical cost, energy, or
Yeah,
time or whatever.
I think it's definitely secondary here. I think it's much lower cost than everything. Definitely than this nophobia, and this like drive to go back. It's obviously a consideration, but I don't think it's a large consideration here. We can obviously again increase the complexity of the model to have also energy cost and also maybe other drives. But here the goal here is to actually try to explain the behavior and to see something with a minimal model. So this is why we try to.
Rephrase my question.
Okay.
Previous, in the human behavior, it seems that energy was an important factor
Yes.
in your model. Here it's not. And this puzzles them. Why there's a difference?
I'll give you like a short answer and a long answer. The short answer is because the people actually were holding their hand like this. And it's very, very hard to hold your hand like this. So energy cost, I think, is definitely a consideration there. And here it's not. And the longer answer is, I don't know, and we can definitely expand this. It's a much longer answer. It will take like at least half a year to develop a new thing. Yeah. Yeah, just information gain. Okay, so that was actually just describing the behavior using the information theoretic principles. Now we try to develop a generative model, which means let's try to reconstruct this behavior from basic principles. And what we did is we did the curiosity loop. So first of all, we want to see again this efficient exploration. How do they know how to explore? So here comes the mathematical definition or mathematical model of curiosity here, which is here we're using reinforcement learning or the actor-critic paradigm, but the reward here is intrinsic and it's related to the novelty flow. So they're trying to learn their environment with this forward model, and in each time step they get this information again on the novelty flow, and now we couple that, we say that the novelty flow is actually equal to the reward in a reinforcement learning paradigm. Which means that after you run this, the policy will converge to a behavior that will optimize getting the information. Okay? So if you start from a random policy, you just go around randomly, you get more novelty using specific actions, and this novelty converted to reward. So you converge to the behavior that gives you the most novelty. And what we did is we did this curiosity loop during what we call the developmental phase until it converges to a behavior that optimizes the learning, and then we use this as we call this an exploration motor primitive, because this is the behavior that maximizes the amount of information on the exploration that you're doing. And good question. The answer is on the next slide. And for retreat, we used for the going back phase, the inbound phase. We use the simple return to home base, which means given the information that you already have on the environment, just plan the shortest way home. So this is very simple. So answering the question, so first you start to explore the environment using the exploration motor primitive. If you get too much novelty, then you retreat. This is what we call the novelty management unit. If you get too much novelty, it retreats. But like they asked, what happens when you actually explore and there's no more novelty in that situation? So then we go to the next level of the hierarchy. And then we develop, we converge a new exploration motor primitive. The interesting thing here is that what you already learned is no longer novel, which means that you need a new behavior to explore the next novel thing. And then we do it again and again, and we did it in 3 or 4 levels, which means each time you learn how to explore one feature of the environment. For example, in this scenario, it was the exit from the home cage because it was the most novel. After you learn that, you need to do a different behavior because this behavior will no longer be rewarding. And then you develop a new exploration motor primitive, which is wall following. And after you do the wall following, the walls are no longer novel. And then you start to go inside. The important thing to understand about this model is that all the behaviors are learned. All the exploration motor primitives are learned from scratch. So for example, the order of exit from the home cage, wall, and then open space is not determined by me. It wasn't pre-programmed. It was emergent from the interaction with the environment simply because the exit from the home cage is the most novel. So this is the first thing they will do because this is the most novel. So all the behavior is actually emerging from this interaction of this model, this agent, with the environment. So this was the behavior of the animal, and this is the behavior that is again generated and learned by the model. And as you can see, it captures almost all the different aspects of the behavior. The exploration from the home cage, going around the circles, and then going inside. And again, I want to stress out, this was not pre-programmed, so everything was emerging from this curiosity loop and the interaction with the environment.
When you have too much novelty, what is the behavioral response? Do you freeze and try?
No. So if you have too much novelty, you engage the retreat primitive, which means that you go back. This was hand design.
Go back and in the mouse behavior, like
They go back to the home cage, wait, relax, have a beer, and then go back again.
and they cannot stay at the home place and just like try like to observe.
They can do whatever they want. This is what they did. Yes.
After the first time that you leave the cage, what's the intuition? Why go near the wall rather than try to climb? It emerges from the model and
Actually, the third dimension I didn't have here simply because the map was two-dimensional. I didn't have the third dimension here. Also, in the original experiment, the jumping was just like in the end. So it's not fully described there, the third dimension.
But what caused this phase position to the other
So,
level?
no.
What's pushing it?
Okay, there are two parameters here. One of them is how much novelty, novelty is greater than some average, then some threshold when you go back. And the second parameter is like a time constant. When you have no novelty for duration for some time constant, then you go up. So if you explore for some time and you don't get any novelty, then you go up.
This was programmed into the model.
This was programmed into the model, but these parameters were also learned. They were adapted and learned and converged. So these were actually not thresholds. They were parameters that started with some value and then they converged to a value that captures the interaction with the environment.
So I'll rephrase my question.
Yes.
So first time that you leave the cage,
Okay.
why turn right rather than go straight?
Because the wall is more novel than non-wall. There's a prior
But
that...
doesn't know.
No. Okay. One assumption which comes in the next slide is actually there is a prior, in our model at least, there's a prior that wall is novel than the non-wall. This is actually coming from physics. Walls are one-dimensional and open space is two-dimensional. So if you just, there are less walls than non-walls in the world. So this is the prior, but we did the full analysis of this. So in the whole model, there are actually only two free parameters. One of them is the sensory uncertainty or the noise in the system, and the second one is exactly what I just described, the prior of the wall probability. Okay, how much probability there is a wall somewhere. And what we did is we analyzed this probability space, and again, for each two parameters, we can generate a behavior. Okay, there's the generation of a full behavior. And then we compared this behavior to individual animals. So usually in the first experiment, they had like 11 animals, I think. Yeah, 11 animals. And they described the average of the behavior. Here we try to see whether we can say something about individual animals in the spirit of computational psychiatry and try to explain behavior using a model and then try to see what you can say something about this. And what we discovered is that using PCA analysis, we actually had 3 different regimes. And one regime is where the animals are actually very scared, or not scared, sorry, very close to the walls. And this is mainly because they have a low wall probability, which means walls are very novel. So they stick to the walls much longer, as opposed to this regime where the wall probability is very high, which means the walls are not that novel and they jump inside the arena much quicker. And we just we found the parameters for each specific animal that best correlates to the behavior against the generative model. And these are the dashed lines are the behavior, and the solid lines are the model. And you can see there are large differences between animals that can be described by simple changing 2 parameters in the model. And these are the only 2 free parameters in the model. So the take-home message from this study is that complex exploration behavior emerges from basic principles of rewarding novelty, hierarchical structure, and novelty management. Obviously, you can add more to this, like other costs, other drives, some utility function. Maybe they're trying to get something else. Our goal here was to see what is the minimum thing that can describe or generate the same behavior. That's what's the goal in the study. So that was about biology and trying to explain it. Now we move to robots. So we try to put the same concepts of robots, in the same models into the robots. So the first question was a very, very, very naive question. What can a robot autonomously learn? So we started from a bottom-up approach. It has sensory and motor information. What can it autonomously learn? So the thing it can learn correlations between sensory information and motor information. So it can just learn correlations between them. So I took the very, very most naive approach. Let's construct all possible combinations between sensory and motor and try to learn them. So we take all combinations, all 2-to-1 combination between sensor and motor data, represent each such combination to like a learning network. I use neural network for this. And we just try to learn to see whether 2 streams of information can predict the other ones. Just learn basic correlations. Obviously, there is no correlation between all of them. So if I wiggle my toe, I don't hear anything. There are some sensory motor streams that don't have any correlation. So I used pruning of the neural networks. Pruning means that you decrease the weights of the neural networks, and after the weights are below some threshold, the neuron itself dies. And if there is actually just white noise, if there's definitely no correlation between these streams, all the neurons will die and the network will just not survive. So there's some networks that survive, and we reintegrate the surviving network's output as another data stream, and then we continue, and then go to 1.
What are the differences between the networks?
Let me show you one slide which is pictorial, maybe to explain. So this is a learning network. I know it's weird that the output is actually going in, but it's a different color. So this, for example, let's say we have 3 streams. We have a camera and a motor command and a motor angle. Okay, these are the 3 streams. So we combinatorically just do all the 2-to-1. These are all the 2-to-1 that you can have. And for example, this neural network actually says, can I predict from the motor angle and the motor command what will be the image of the camera? So I just construct all of them. I do the learning and pruning concurrently. This, let's say, just an example, these 2 don't survive, and this one survives the pruning, which means there is some correlation here. And then I take in the output of this one as another data stream. Again, construct everything and do the same process 3 times. I still have a question? It's just the output of the data stream. So for example, the output to here is actually the image of the camera. And the output here is the motor command. Okay, because again, I know it's weird that the output actually goes inside. Here? Yeah, okay, I understand. So this is actually the prediction. Now, there is a training phase and an execution phase. So during the training phase, you have the motor angle as the train set, okay? And then the prediction of the motor angle. Exactly, yes, exactly. The prediction. Thank you for asking. So I used this robot because I was still in Weizmann and not the Media Lab, so we had only Lego Mindstorm and not really cool robots. So this robot has a 1 degree of freedom motor for the camera, so the camera can move, very important. 1 degree of freedom for the arm and the brain. The brain comes separately from the Lego Mindstorm. And the data streams are the motor command to this the motor command to this motor, the motor command to this one, the motor angles. You get all of this free from Lego, thank you. But we take 2 time steps, obviously because we are interested in internal models, so you need 2 time steps, and they're just pixels from the camera. So all in all, we have 8 data streams. Okay, does this answer your question? Yes. Okay, so we have just 8 data streams. If you do the combinatoric of all the 2-to-1 correlation of 8 data streams, you end up with 168 networks. So I trained 168 neural networks running in parallel for several 100,000 time steps, and only 9 survived the pruning. And this is very nice because these 9 actually have a very basic structure. It's just the internal models. So for example, this one, given the current position of the motor and in the previous position, what was the motor command? It's called the inverse model. This given the current command, the current position and the command I did, what will be the next position? This is the forward model. Most of the people forget that there's actually a third one, which is predicting the past, which is giving the place I'm here and the command I did where I was before. So these three for one motor, these three for this one, and these three are the interesting ones. What does this mean? Given the pixel, the color of the pixel now and the color of the pixel before, what was the motor command to the camera? Okay? So if they're the same, the output is 0, and if they're different, they're 1. This is actually motion detection. Okay? The rationale here is that if you move the camera, most of the pixels change most of the time, and if the camera is still, most of the pixels are the same most of the time. And this is what it learns. When I sent the paper out, the actual reviewer said that's the first time someone learned motion detection, and I was surprised, and then I realized why. This is a minus sign. It took me like 100,000 time steps of neural networks to learn x minus y. And the basic principle here is that even though this is the simplest calculation you can ever think of, I don't want to have any pre-programmed thing, even a minus sign. I want to learn everything from scratch. So that was very interesting. Another nice anecdote, how research influences your life. So initially I ran this experiment, and the robot didn't learn anything about this. I didn't understand why, and then I realized that it stared at a blank wall. It was a white wall. You can't learn anything if you're just staring at the white wall. And then I put like a cluttered environment. It was very nice. It learned. And then I went to my child's room, and I saw blank walls. I said, oh my God, my child can't learn emotion detection. So I put Winnie the Pooh all over the place. So she's okay with motion detection now. Another small anecdote is that if you notice, this is the only mapping that is not linear. All the other ones are linear, in some sense. So when you get that, you'll immediately think of there's a bug. But then you think about what it means. It's the forward model of the camera, which means given the current pixel and the motion of the camera, can I predict the next pixel? So if the camera doesn't move, yes, I can. And if the camera is moving, I have no idea, so it's 0. So that actually makes sense. And this is the internal model of the camera. So I took these 9, plugged them into the new data stream, the output of them to a new data stream. Obviously, I didn't do anything, because if I have 17 data streams, it's too much. So I just maintained only those that have at least one arm and one camera in them. And only one of those were those new ones. So I had all in all 72 new networks that were learned, pruned. 5 survived, but they were functionally completely identical. And what they had is the camera. The camera now is a 7x7 RGB patch. And there's something about our motor command. And the output is the motion detection. So is this pixel 0, 1. This rationale is if I move and something moves in my visual field, that something is me. So that's actually visual self-recognition. So as you can see, there's a white where there's a robot, and there's black where there's no robot. So the robot learned how to recognize itself. So there was, at some point, a huge hype about robots staring at the mirror and learning about themselves. It comes naturally if you just do the second-order correlation between the sensory motor information. That was very nice. And then I took, again, this one, plugged it in again. And the third level was actually, so now we took the whole image. So I did a self-recognition map. So this was the input to the network, and the output was the arm motor position, just the angle of the arm. So this is actually means that because I know where my arm is in the visual field, and I know my arm in the arm coordinates, I can actually learn the vision to arm coordinate transformation. I can transform each coordinate in my visual field to arm coordinates. So again, it learned it by itself. I didn't, again, very important stress, I didn't tell it what to learn. This was what survived the pruning. So this is the only thing that it can learn. Everything else just didn't survive. So every time I'm doing this research with robots and learning, the people ask me, so what does the robot do? I say, no, it doesn't do it. It's like curious, it's learning. I say, no, but robots should do something. And no, it's learning, it's going around, exploring. No, it should do something. A robot should do something. Yeah, I know, but it's do something. So I said, okay, let's do the same exhaustive thing and see what can this robot do with all the things that he has. So I constructed all the networks, all the possible networks of all the things that it learned, and there's only one network that survived, which is a non-trivial network, which means a non-trivial closed loop network, which means there's a sensor in the beginning and a motor in the end, and only networks that it learned. And this is it. Let's see if you can see what it means. So you put the camera in, you put some delay. There's a visual change detection. It learned already motion detection. So this means there's now a map of things that moved in the environment. You take that thing, transform it to coordinate transformation. So now if something moved in the environment, you know it in arm coordinates. And then you plug this into an inverse model of the arm. And the arm moves there. So I don't know if you know what this means. This is reaching. So if something moves, the arm just goes there. And that's the only thing that this robot can do. But still, nice. So this is like this blue thing is moving, and the arm is just following it. But the nice thing about autonomous learning is that if something goes wrong and it's still learning, it can recalibrate. So for example, this black line and the gray line means that I changed, for example, I deleted the red channel of the camera, and I changed the maximal power to the motor. And as you can see in the middle, it's totally scrambled. It doesn't understand, and something is wrong. But because it's continuously learning all of these mappings, it completely overcomes everything, and then it comes back again to full reaching motion. No, this is a robot. This is a real robot that ran for like almost a week, and it actually ground the plastic of I had like a white powder beneath the Lego Mindstorm. It was horrible. But again, the whole point here is that I didn't tell it what to learn, and this is the only thing that it can do after like the 3 iterations of learning. So that was really nice, but actually this is not curiosity. This is just stem-cell learning, because curiosity is about learning how to explore. So let's say, so I'm going to like have a pop quiz for the audience. So let's say we want to learn coordinate transformation. So remind you, I know where my arm is at the coordinates in the visual field, and I have the motor arm command, the motor angle. How should I move the arm in order to learn this transformation? I will give you 2 wrong answers. One is don't move the arm. That's a wrong answer. Another wrong answer is move it randomly. You will learn everything, but this is not the optimal way to learn this transformation. So can you think of how you move? You don't need to answer. You can just move your arm. I will see it from here. How should you move the arm in order to learn this transformation? Yes, wake up. Thank you. Good. You should just scan the entire visual field, because this is the optimal way to just learn, because you just scan the visual field. So you should know random is like a random walk, it's square root of n. This is n, it's just much faster. And the nice thing, I just ran this curiosity loop. Again, I ran the curiosity loop where here the reward was the prediction error of the neural network, which is how much it learned. So I put the prediction error as the reward for this curiosity loop, and the robot learned by itself to move across the entire visual field. Again, I didn't tell it how to move. This is what it learned how to move. Almost last pop quiz. Let's see, now you want to have this learning self-recognition. So again, remind you, if something moves in the visual field, and I move in the visual field, that something is me. Now it's a tougher question. How should you move the eye and the hand? You have full control of the hand or the arm. How should you move the arm and the eye in order to learn this transformation? Someone? Yes, this is almost correct. So what you should do, you shouldn't move the eye, because if you move the eye, everything is motion detection. I mean, you get just everything is white. So you should not move the eye too much. You should move the arm, because that's your signal. You want to learn to move the eye. And what you should do is you should keep the arm within the visual field. So if I do this, this is also not good. So what I should do is something like this, okay? Or like infants, or drunk people, like, oh my God, this is so cool. Okay, so you do something like this. And as you can see, if I compare like the random behavior, just total random, and what the robot learned, again, the robot learned this behavior. I didn't program it. It learned it from this curiosity loop. It's much, much better. And if you have enough imagination, then you may think that this robot actually behaves like infants in a certain developmental stage when they actually look at their own body. There is such a developmental stage. You have enough imagination, you can think that this robot behaves like an infant in some developmental stage. And this model can try to first explain maybe why they're doing that, because it shows that this is the optimal way to learn self-recognition. But even more than that, this model and the whole model actually suggests a sequence of behaviors, because you have to learn motion detection before you learn this, and you have to learn this before you learn coordinate transformation. And each one of those, if you run the curiosity loop, actually results in an optimal behavior. So there's a sequence of optimal behaviors that must come in order. So this can maybe teach us something about infant development. So complex infant-like robot behavior emerges. Again, everything here is emerged. I didn't tell it what to learn, or how to move. Everything emerges from these basic curiosity loops. Emerges from basic principle, which is exhaustive construction and pruning of learning networks. And again, in the brain, it's called exuberation for some reason. And you have hierarchical structure and rewarding novelty again. How am I on time? I'm not on time. Good. 1 minute this, 2 minutes movie, and I finished. So now I want to move about a robot that learns to engage people. So this is our cute Dragon Bot. This is the robot we have in the Media Lab. It's very, very nice. And it's very, very cool. It has a lot of facial expressions. It can be sad and happy. So I use reinforcement learning again. But now the reward is engagement. And engagement here is just the number of faces you see. The more faces are looking at him, the more reward it gets. And the question is, which facial expressions actually keep people more engaged? So again, last pop quiz, it can do like a yes, I like it, sad, sorry, and shy, yawn, like this. Which one of these behaviors will keep people most engaged? Like, will make people not leave him? People with children. Huh? I like it? Okay. So the correct answer is sad. So no one leaves a sad Dragon Ball. If anybody with infants know, if a baby is crying, no one leaves it. And we actually have data for this. So we time align to the execution of the behavior. And we measure the change in engagement, which means how many faces were added or subtracted. And STAD was the only one that after 25 seconds, no one left the sad thing. And again, I was there. It was the World Science Festival. Everyone, regardless of age, gender, race, when it said like this, they would say, oh, what happened? Did he sad? And they reacted to it. And again, using this reinforcement learning, actually the action value after 2.5 hours, the robot discovered this and actually just made more sad faces than every other thing. So this is so cool. So even social exploration can be autonomously learned, and you can, again, take it back to home. Don't leave your sad baby, because actually it will learn to make it more. Never mind, that was. I'm going, man. I have a movie of 2 minutes that explains the recent research. I have 2 minutes? I don't know. So I can do it? Okay. So this is the music. It's actually a story about the music, because in MIT Media Lab no one recognizes this song.
I am Paul. Nice to meet you. We are going to play word games together. The story is called The Bird Lost Her Ball. You move the characters around, and I will tell the story. I don't know the words. Can you show it to me? I'm routine with the puns. I wonder what will you do now? I love trying new things. Can you move another character? It would be wonderful to play again sometime. See you, bye-bye.
So if I learn something in Media Lab, to make cool movies. That's what you learn in Media Lab. So I won't go into. So what you saw is actually that the children were more curious after interacting with a curious robot. So, but it only those aspects that it actually did. So it explored and it said having new things, but it didn't ask any questions. So the question generation aspect was not different. I don't have time to talk about these equations, but also the robots optimally learn the reading skills. So the whole experiment was about teaching the children new words and wanted to personalize the interaction. So we assessed the reading skill using maximizing expected information gain. And this is this. So the take-home message is that children's curiosity may be promoted by interacting with a curiously behaving robot. So to summarize, I introduced the model as a novelty as intrinsic reward and hierarchical structure, and this results in emergent exploration motor primitive and the novelty management, and it can reconstruct a complex exploration of robots, of rodents, and also infant-like behavior in robots. And child-robot interaction, you have like promotion of children's curiosity. Turning back to the question, is what can limit exploration? Maybe processing costs. Novelty management and maximization of novelty signal-to-noise ratio are maybe the guiding principles of exploring animals. And one can learn to explore by having these curiosity loops. And and social interaction can actually increase curiosity in children. So future work, I want to extend the model into some other aspects of unsupervised learning and reinforcement learning, because up until now I had only supervised learning as the reward, learning the reward. And because I used only 1 degree of freedom, 2 degree of freedom robot, obviously if I have more robots and you have a lot, you cannot do an exhaustive search of everything. So you can have this. I'm starting to work with infants, so this is my 3rd child now playing with DragonBot. And we want to have also some sort to optimally assess the child and actually guide this behavior using this, based on this model. And robots, we want to have more robots, because this is next year, it's very cool, it's playing with DragonBot here. And the vision is to understand many aspects of interaction and also interaction with curiosity with other drives. We have the social drive to be in group and stuff like that. Behavior, to map mental syndromes to model features. Again, as I talked in computational psychiatry, to have like model parameters define specific individual behaviors, and to generate maybe a model-based enrichment programs. And for robots, we want a robot that learns people and vice versa. And thank you very much. Question?
Question?
Yes.
About the result of the robot that is called
Yes.
Caroline.
Yes.
So, to what extent, I guess this is a real hardware robot.
Yes.
What did you learn from this rather than from simulation?
Okay, a really good question. So, okay, I actually tried in the beginning to use, in the curiosity, for example, thing, I tried to use the prediction error as the reward, because that seems like a good thing to do. But because it wasn't a simulation, there was a lot of noise, and there's a lot of problems. So actually, if you think about it, prediction error is not a good thing to use as a reward, because you can reach a point when you have too much noise that you cannot learn. The prediction error will always be high, and we actually don't learn anything. So, I learned that in simulation you can obviously inject noise, but this was actually just came from the interaction with a real robot. So what I changed there is actually not the prediction error, it's the change in prediction error. And the change in prediction error overcomes this problem of noise, of real world noise. So I changed from prediction error to the change in prediction error as the reward. And again, you can obviously inject noise into it, but I just wanted to see a real environment. And again, what I said, for example, suddenly figuring out that the background is not cluttered enough. Again, you can obviously simulate different environments, but only when you start to interact with real robots, you start to see all the problems. This robot is very simple. There's actually a lot of simulations of Lego Mindstorms. There's actually a lot of simulations of the iCub, which is like a 70 degrees of freedom. But still, when you come to this, the thing I learned from Media Lab is that if it's different with real robots, they actually break all the time. And that's something which is maybe not nice, but it's something that you have to deal with.
I have another question. You said that the mice looking for novelties around, they moved to the wall because it was more novel there. You describe it as 2 dimensions, 1 dimension. I suggest maybe they go to the wall not because it's novel, just because they're afraid.
Yes.
Mice in the wild, they go.
I had a lot of discussion with the etologists about why they go along walls. So there's some basic thing that biologists will say, it's more safe. Like evolutionary, it's just better to be along walls because it protects you from predators. So this is one thing. We suggest an experiment, we didn't run it yet, that actually can differentiate between the two, which is, again, because my model is actually an emerging property. So going along walls is an emerging property. It's not like pre-programmed in the brain. So my prediction of this thing is that pups, just the pups that start to walk the first steps, will not go along walls. Because if it's genetic and just described to them, it's just going along walls because evolution made it so, then even a pup that encounters the world for the first time will go along walls. And if it's an emergent property and it's learned, then it will not. We didn't run this experiment yet, but this is prediction.
May learn is that it's safer to be near the wall.
Yes. But if it's
Not because it's
okay.
So the control unit there, you answered Jonathan before that there is nothing interesting in the middle.
Yes.
So make it interesting.
Yeah. Again, this
You
experiment.
can still go to the wall because the wall is safer.
Yes. The main manipulation that you can do in order to test this model is during the development. So for example, another prediction is that if you raise pups with a very, very cluttered environment, very cluttered in the sense that the prior of walls is actually higher than non-walls, then this behavior will be completely different. There's, again, this was just a first try to explain this thing. There's a lot of things to try to, a lot of new experiments that come up from this model, which is a good thing for a model.
A related question related to what Chaim asked.
Which one?
The last one.
Okay.
Why use robots when you study children's behavior?
Because
Especially
children love
older
robots.
Sorry?
Children love robots. That's the short answer. The second answer is that there were actually a lot of experiments comparing children that played with, no, not a lot, but several experiments that children learned from a virtual agent and the children that's learning from robots. And the actual physical embodiment makes a difference. There's, again, the whole human-robot interaction field shows that you can actually learn more. There are more learning gains, but there's the physical embodiment of the robot. We did some experiments just in the lab also with other robots.
So your interpretation of behavior in an elevated classmate would be the
In a what? Sorry, in a what?
So the test called elevated classmate.
Okay.
Used to test anxiety.
Yes.
Also two closed arms with walls and two open arms. So your interpretation of the preference for the closed arms would be that this way they might gain more information. If they want to be open arms.
I'll tell you, this experiment was very unique in the sense that the only drive that they had was curiosity because they were like safe. They had a home cage with everything. Or the forced experiment, when you take your mouse and just put it somewhere, I'm not sure curiosity is their main drive of like trying to explore things. I would be very cautious to say that there's not another drive, like fear or like other that drives them to do something completely different than just freely explore and try things. So I wouldn't take my model to a very, very structured experiment when you actually like take it out and have a lot of other factors than just free exploration. This is why I use this experiment to try to explain, because it's so clean in the sense that there is nothing else. It was like dark. There was no smell. There was nothing there except going out for explore. So I'm not sure this simplistic model can explain that behavior.